Please go.
All right. So, hello everyone. I am Laura Fonda, and I will be presenting on to pay or not to pay attention, classifying and interpreting visual selective attention frequency features. I know there's quite a bit to unravel here, so let's get started. All right. So I know a lot of you are not in the neuroscience field. I will give a definition of attention that is more relevant to the paper, and that is attention is the efficient use of limited computational resources in the brain to filter the vast majority of the stimuli that we receive on a daily basis. It's important to study attention because it's important to remove these hard-coded biases that are translated to and are used as a measure of intelligence. And this phenomenon is known as attentional blindness. Attention is related to each modality, but today I will mainly focus on the visual selective attention, and in more detail, the visual selective attention to target or distractor objects. To give you more intuitive understanding of what I'm talking about, I'll try to do a little illustration. So in the following slide, try to find these blue glasses that are left in this very cluttered desk. And while you do that, try to see where your, I think somebody is writing on the screen, but I don't know how to clear that. Okay, good. So as I was saying, try to find the blue glasses in the following slide. But at the same time, try to see where your eyes are wandering in the next screen. I'll give you about 5 seconds. Okay, that's time. So as you can see, the blue glasses, which I have hidden a bit more, made a bit more difficult to see, are the target objects because you want to find them. But while looking for that target object, you might have been distracted by 2 possible distractor objects, if not more. One are the glasses, the black glasses, because they have a similar shape to your target object. And the other could be these chains that are similar color as your target object. So, okay, you might be saying, fine, Laura, this is a very cool illustration, but what are the numbers? Where is the data? How can you quantify any of this? Attention in general is measured with electroencephalography, which is a tool that measures cortical activity using electrodes and a cap that's placed on someone's head. It has a very good temporal resolution, which makes it good to acquire the attentional dynamics. But unfortunately, it has a very low signal to noise ratio. So it requires a lot of pre-processing and very careful acquisition for analysis later on. A measure for attention is N2PC, which is the standard for attentional selection. And it is the cortical correlate of attentional selection that's extracted from EEG. It's not very robust, but it does require few electrodes. As seen here, it only requires a few electrodes in the back of the head. And that makes it more or easier to calculate. Another method is electrical neuroimaging, which uses the full cap with all of the electrodes, which can make it a bit more limiting, but it is more robust. Classifying attention, on the other hand, is not a very well-developed part of attention, but a few groups have been able to classify attention, whether it's the location of attention or to compare and contrast if attention is being paid to a target object. To advance this, for my master's thesis, I was able to compare, classify target, distractor, and baseline attention using logistic regression and SVM with the discrete cosine transform extraction of EEG signals. I will not go too much into detail about that because this is quite a short talk, but it's all within the paper. The main thing to understand here is that logistic regression and SVM performed quite similarly. And if you can use a simpler method, it's easier. So what we decided to do now is to take this understanding of N2PC, that we know that N2PC electrodes contain the most discriminable information because they're successfully used in previous work. But what hasn't been done previously is the interpretation of these classifiers on their decision-making and feature importances. Not any of the previous works have worked on interpreting these classifiers. So this begs the question, how did the classifier learn to discriminate the target, distractor, and baseline features, particularly for my previous work? And which features are the most important for the classifier to arrive to that decision? In order to answer these questions, we have laid out a methodology, as you can see here. The part on the left is detailing what prior works have done up until classification with logistic regression, as it performs just as well as SVM. And what we decided to do here is to replicate this classification, followed by interpreting the logistic regression classification weights for all of the features. From there, extracting and selecting which features have the highest weight in the classification, and then reclassifying the logistic regression classifier, relearning, the logistic regression classifier, and comparing the performances between the original and the retrained classifier. So to understand a little bit how to interpret the logistic regression classifier weights, it's important to understand what or where the classifier weights come from. As logistic regression is not simple like linear regression, what is necessary is to take the resulting coefficients, which are the odds ratios, and exponentiate them to convert them to regular odds. And this is seen in equation 1, which from then it leads to this definition of how to read the odds, which results mainly in if the odds are greater than 1, then a high value of that feature connected to that weight leads to a higher chance of that feature belonging to that class. And if the odds are less than 1, then a high value of that feature leads to that being classified as not part of the class. So what we really want to see in the results of the classifier weight interpretations is the amplitude and the value with respect to 1. It's important to note that in the logistic regression classifier that we decided to use, we use the 1 versus all approach, which in the end, for a 3-class problem, results in 3 classifiers, thus 3 sets of weights, classification weights. And that's what we will be showing right now. So for the first results on interpreting the baseline classifier features, here we can see the one-dimensional coefficient weights or the odds. And you can already notice that there's some sort of periodic pattern happening. And what we decided to do is to take this one-dimensional coefficient weight of the baseline classifier, which is one of the 3 classes, and turn it and restructure it to look at the weights by electrode. And this looks something like this. Using this graph, now we can compare the N2PC region electrodes from the rest of the non-N2PC region electrodes to see if there is some pattern emerging. And already from this, we can see that the N2PC region electrodes overall have a stronger odds ratio compared to the non-N2PC electrodes, as 1 is here. And Yeah, that's true for the baseline classification. In addition to that, the DCT bins from 0 to 7 in the baseline classifier have the most discriminative information. Since they are under 1, they are discriminative as in if a feature is high in this region, then it is likely that it will be classified as not baseline. We applied the same logic for the target classifier coefficient weights. We restructured it to electrodes, and here as well we can see that the N2PC have higher odds, not odds ratio, that's an error, higher odds compared to the non-N2PC electrodes for the target classification. And additionally, for these deep pins 0 to 7, it seems to have quite a high strong information, which makes it more discriminative for these features. We applied also the same logic for the third and final class, which is the destructor classifier. And here we are also able to see that the N2PC electrodes, which are the darker ones, do have a distinct pattern that is different from the non-N2PC electrodes. And so we can say that the N2PC region electrodes overall have higher odds ratio, particularly towards the higher frequencies, the higher DCT frequency bins, although it seems to be less than the target and also baseline classifier. What we also noticed is that the features from 120 to 149 have the highest or the strongest odds for the N2PC region. Then we decided to only group the N2PC electrodes to try to really see what is the pattern of all of the classes looking like. And from this, we were able to understand that indeed all of the N2PC electrodes overall have stronger odds compared to the non-N2PC electrodes. And additionally, the fifth and final evidence that we found was that for some reason, between 20 and about 60, there seems to be quite a high odds from the coefficient weights, which correspond to frequencies 60 to 360. We decided to threshold at plus or minus 0.004, and whichever weight passes this is the weight that the DCT frequency that we will use in the future classification. This resulted in these DCTs that you can see in this range here. As a result of reclassifying using only the N2PC electrodes and only the top DCT frequencies that emerged from the thresholding, we were able to decrease the feature vector from about 20,000 to about 1,400, which is 7.3%, I believe, of the original feature space for an accuracy loss of only 0.04, which I believe is quite successful. So to highlight the evidences that we found, one, N2PC regional electrodes overall have a higher odds ratios compared to the other electrodes, which makes sense and follows the traditional methods. The DCT bins from 0 to 7 in the baseline classifier have the most discriminative information for that classifier. And additionally, the same applies for the target classifier. And these are all things that we expected because the DCT bins 0 to 7 correlates to frequencies that are previously known in attention to be related to selective attention. So these features should actually be of higher importance for attention signals. In addition to that, we found two evidences that were a bit more odd and require further analysis. One was that for the distractor classifier, the DCT features from 120 to 149 had the highest discriminability information. This is very odd and likely an artifact because these are features that relate to about 500 hertz, and this is not some frequency range that is necessarily known for brain activity or attentional activity particularly. In addition to that, the DCT frequency bands 20 to 80 had quite unexpectedly high odds as the frequency ranges from 60 to 360 hertz, which is what 20 to 60 relates to, have never before really been used to study attention. They have been used to study higher cognitive loads, but not attention. And so this is something that needs to be further analyzed, as it might lead to a better understanding of what exactly attention frequency ranges hold. And that is all. Thank you very much. And I'll take any questions or comments that you have.